Hello, students. Today, we are going to look at a topic that sometimes feels a little difficult, but is actually behind a very common experience. We are talking about the Nernst equation. Now, what if I told you this equation is the reason your phone battery percentage goes down? Let's begin.
So let's start with a very practical question. You see a new battery, and the box says it has a standard cell potential of, say, 1.1 volts. But after you use it in your remote or your toy for a few hours, you check, and it's giving only 0.9 volts. Why does this happen? Is the battery faulty? Well, not at all.
Okay, the answer to this puzzle lies in today's topic. The Nernst equation is what helps us move beyond those ideal, standard conditions you read about in the textbook and into the real world. Let's see the core idea.
Right, so at the simplest level, what is the Nernst equation telling us? It just tells you how the voltage of a cell will change when the concentrations of the chemicals are not that perfect 1 molar that we assume for standard conditions. That's it. It connects the voltage to how much chemical fuel is actually left inside.
So let's imagine a battery in your flashlight. When it is brand new, it is full of reactants, right? So the chemicals are fresh and plentiful. This means the voltage is high. Now, as you switch on the flashlight, these reactants get used up. They are consumed. And as they get consumed, the voltage slowly starts to drop. The Nernst equation is what helps us calculate this drop precisely.
Now, for your exams, this is the definition you should remember. The Nernst equation relates the cell potential, E, to the standard cell potential, E naught, and the concentrations of reactants and products. It is the formula that connects the ideal voltage with the real voltage that you get in practice.
Okay, to make this concept very easy to remember, let us use an analogy. This will help the idea to really stick in your mind.
You can think of the Nernst equation as being like a special kind of thermometer, but instead of measuring heat, it's measuring how tired a battery is. It's checking the chemical energy. Let's map this analogy properly. See, a high temperature reading on a thermometer means something is hot, full of energy. Similarly, a high voltage means you have a fresh battery, full of reactants. Now, as the temperature drops, it means energy is being lost. And just like that, as the battery is used, the voltage drops. Finally, a low temperature reading means it is cold, and a low voltage reading means the battery is tired, almost dead.
So, why does this matter so much? Because in the real world, our batteries are almost never operating at those perfect standard conditions of 1 molar concentration that we learn about. The Nernst equation is the tool that lets us calculate the cell potential under any concentration, which is what we need for practical applications.
All right, so the voltage drops as reactants are used, but let's build a clear mental picture of this process. Let's visualize a battery's life in 3 simple snapshots.
So, snapshot 1, a fresh battery. Imagine a Daniell cell. The copper sulfate solution is a bright, vibrant blue color. This deep color indicates that the concentration of our reactant, the Cu2+ ions, is very high. And look at the voltmeter. It is reading the full 1.1 volts. Perfect.
Now, for our second snapshot, the battery is half used. What do you see? The blue color of the solution has become lighter. This is because some of the copper ions have been consumed in the reaction. Since the reactant concentration has gone down, the voltage also drops. The voltmeter now reads 0.95 volts.
And our final snapshot, the battery is nearly dead. Look at the solution now. It's a very pale blue, almost colorless. This means the reactants, the copper ions, are almost completely depleted. And the voltage? It has dropped all the way down to 0.80 volts. This visual change perfectly illustrates the Nernst equation in action.
Okay, so we have understood the principle. Now let us see how this equation is used in real-world technology.
First, let's look at a very interesting case, a concentration cell. You might think, if we make a cell with 2 identical copper electrodes, the standard cell potential, E naught, should be 0, correct? So how can such a cell produce any voltage at all?
Well, the answer is that it is the difference in concentration between the 2 solutions that drives the reaction. Even if the electrodes are the same, a difference in concentration is enough to create a potential difference. And the Nernst equation is what allows us to calculate the exact voltage produced based on the ratio of the 2 concentrations.
A very powerful and common application of this principle is something you see in every lab, the pH meter. This is a perfect real-world example of the Nernst equation at work.
So how does it work? It is quite clever. First, a special electrode which is sensitive to H+ ions is dipped into the solution.
The concentration of these H+ ions changes the electrode's potential. A voltmeter inside the device measures this potential difference. And finally, the device uses the Nernst equation to convert this voltage reading directly into a pH value that you see on the display. It's basically a concentration sensor.
So, we started with a mystery about why a battery's voltage drops, and we have found the solution. Let's do a quick recap of the most important things to remember.
So, please remember these three key things. First, the core idea. A cell's voltage is not a fixed number. It always depends on the concentration of its reactants. Second, the mental image. Think of that blue copper sulfate solution fading as the battery is used and the voltage dropping along with it. And third, the key application. The pH meter, which uses this very principle to measure concentration by simply reading a voltage. If you can just hold on to these three things, the core idea, that one mental picture, and that one application, then I assure you the Nernst equation will feel much, much lighter in your exam. Keep studying, and I am sure you will do very well.